No mai haere mai ki te whare toi, nā reira, tēnā koutou katoa. Ko Graham Frost tōku ingoa, he matanga hotaka hapori mō te whare toi. Hi everyone, my name is Graham Frost. Apologies for the garbled introduction. I'm the Public Programs Coordinator here at City Gallery Wellington, and it's my pleasure to welcome you all to the first City Talks for our year of 2024. So it's been a long day. Welcome everyone, and it's so great to see this auditorium full again, with a really invested audience that have been coming back, and kind of really appreciating this relationship between City Gallery Wellington, Te Whare Toi, and the New Zealand Institute of Architects. I'm not going to take too much of your time. In a moment, I'll invite tonight's presenter, Ewan Brown, to come up. But just before I go, I'll just give you a couple of very basic sort of housekeeping pointers. It's really unlikely that we'll have an emergency. If we do, just please remain calm, follow my instructions and the instructions of our staff in the space. We won't be evacuating through the emergency exit at the far right. That space, that entryway is no longer accessible. So instead, we'll be heading out through the doors that you came from, turning left, and then just heading out to Harris Street. If you need to use the restroom of Wharepaku, there is a set of restrooms just on your right as you come out of the doors at the far end of the corridor. And do stick around for some drinks and refreshments after the talk as well. So without further ado, I'll invite Tina Williams from the Wellington branch to introduce tonight's speaker. Thank you so much, Tina.
Tēnā tātou katoa. Welcome, everyone, and Happy New Year. I know it's March, but this is the first time we've seen you all this year, so welcome, and thank you for coming. Tonight, we're kicking off with one of Wellington's foremost architects. Ewan Brown is Managing Director of architecture firm Tennent Brown, an award-winning practice with projects ranging from residential to commercial to education and more. No doubt for many of you who dwell in Wellington, you would have stumbled across the latest curiosity on Kelvin Parade, the Living Pa, which is poised to be the new gold standard for sustainability in Aotearoa. But first, Ewan is starting with carbon, the most talked about element on the periodic table in recent years. Its permutation through every aspect of the built environment is calling for urgent and careful consideration as the climate crisis becomes ever more tangible. Buildings and the construction industry are globally responsible for an estimated 28% of carbon emissions from operational energy and 11% from materials and construction. At the end of 2022, the UN reported that CO2 emissions from building and construction hit new highs, leaving the sector off track to decarbonise by 2050. And New Zealand is no exception, with associated emissions also on the rise and the construction and demolition waste accounting for 50% of New Zealand's total waste. So, hopefully I haven't put too much pressure on Ewan, and you'll all join me in warmly welcoming him to the stage now. Thank you, Ewan.
Tēnā koutou katoa. No koti rana, no inarani okotapuna, te Te Ao Māori taku manawa, I tupu aki ao ki raro I te maru o wharete, I te taha o te awa o Manawatu, kei ponaki ao I noho ana I mahi ana, anaine, ko Ewan Brown aho, tēnā koutou katoa. Thank you, Tina, for that fulsome introduction. I did have some trepidation when Tina originally asked me to do this, and I'd have to say in the last couple of days I was asking myself again, why did I say yes? But I figured out there are two reasons. Firstly, as Tina said, construction is responsible for 39% of greenhouse gas emissions globally. So that's the embodied and the operational together. So that's a lot of carbon. And there's a lot of evolving data and tools that we use. And so it's really important that we get all this resolved. We won't be able to get all this resolved in the short term, but we need to work on the trends. So we need to act now. The other reason is we need to raise awareness, and this is my attempt to do that. So we need everyone in the construction sector, particularly, to get some carbon literacy and to improve how they're doing and start using that understanding. So I have some carbon experience. I'll show you a couple of projects. So I feel I can help, and it's my job to do that little bit of help. So hands up, anybody here who's done an LCA, a life cycle assessment, just to assess. Oh yeah, there's one or two. Nobody from my office has admitted it. Oh yes, there we go. There's Caitlin. So what I'm trying to do tonight is talk to two groups. So to those of you who haven't raised your hands, those who are starting on their journey, I want to be able to sort of show you some basics. But also there are others who have got more experience, and we need to challenge those people and myself as well. So I'm sort of covering quite a lot of detail in a very short time, and it is quite a dense topic, so my apologies for it being a little dry in places. There's a lot of graphs, and I don't think Kevin's here, but Kevin was going to heckle me about graphs. So there's quite a lot of complexity, but I still think it's important to go to this level of detail. Start using this thing. So, very basic slide. So a couple of things before I start. One is that we all need to be going in the same direction. We need to make sure that we're not fighting about the detail, that we're moving in the direction of the trend of information towards getting to carbon neutrality by 2050 is going to be very, very difficult. So everybody's got to work together in the same direction. There are disagreements about tools, what we measure, the data. And the second thing is I think we need to be positive. It's very easy to get depressed, and my apologies, my first 5 slides are a little bit negative, but that sets the context. But I believe things are possible, and I also think with climate change there's 3 groups of people. There's those who think technology will solve all our problems, and so they don't think we have to do too much. There's also a group that think we're a bit screwed, and there's no point in doing anything because we won't be able to solve any problems. I put myself in that third group in the middle, which is hopefully not too small, and encourage you to come to that group as well. That it might be very hard, and some of the answers may look a little bit impossible at the moment, but it's worth trying. So I first became involved with carbon in about 2014, when Hugh and I were working on a project called Ngā Purapura in Otaki for Te Whangarokawa. And we didn't have any data numbers, but we had heard that steel was high in embodied carbon and timber was low. So on that project we did exactly that. We tried to minimise steel and maximise timber, but we still had to learn about concrete, so there's a bit of concrete in that building. Then about the same time we started working with Ngāi Tūhoi, and 2 projects for them, and they were Living Building Challenge projects. And as part of the Living Building Challenge, you need to do a full carbon analysis, an LCA, a life cycle assessment. So we worked to a certain level on those, but Tūhoi stopped the process for Living Building Challenge on both those projects partway through. So we didn't complete our carbon assessments there. But shortly thereafter, we worked on East Gisborne Airport with Eastland Group. And Caitlin here, Caitlin there, put your hand up, Caitlin, I was going to embarrass you. Caitlin worked on LCA Quick with the Brands' free spreadsheet tool, and we analysed some steel portals and some steel purlins for the building, transferred them from steel to timber and saved 34 tonnes of carbon. So we started learning about the numbers then, but we didn't really know what the whole building carbon was. So later on that project we employed a firm called eTool from Perth, and did a full LCA across all the modules, which I'll talk about shortly, and understood more about the carbon on that project. And then after that, we've done 3 or 4 more eTool LCAs, so an external provider. Caitlin has done Brands LCAs for other architectural firms, and we've also brought on One Click LCA to the office about a year ago, and so trying to bring that through the office as a business as usual tool. Everybody who's drawing is understanding how LCAs go together because it's a plug-in to our drawing program. So my discussion's got 5 parts. One, I'll talk about the global context and tell you why carbon is an issue, in case you don't already know. And then 2, I'll define a few common terms because there's a lot of jargon as well. 3, I'll explain why it's an issue for us in New Zealand. 4, I'll show you what we're doing in our practice, 2 projects which are really pushing some boundaries. And lastly, I'll give you some tips or some thoughts about what we can all do. Consultants, public, contractors. So to start, those 4 slides, or actually 5 slides. So this slide sort of shows carbon in the atmosphere from 800,000 years ago to 1700 AD, so 278 parts per million on average through that period of time. So that's before the Industrial Revolution, but since 1700 and intensive human activity, it's gone from 278 to 421 parts per million and rising yearly. I actually looked in the weekend, it's 424 now. But so that's an increase of 50% in that period of time. And so this next slide is from IPCC, Intergovernmental Panel on Climate Change, their data. And it's part of their conclusion that humans are responsible for climate change. And I also note here, I've been reading recently, that half the greenhouse gases emitted since the beginning of the Industrial Revolution have been emitted in the last 30 years. So we've got a couple of hundred years since the Industrial Revolution, but then half of those emissions have been in the last 30 years. This slide shows the IPCC 5 scenarios, depending on what we do and we don't do. The decade we're now in will decide, it's critical to how children will live, how much rain will fall, and how hot it will get. We're now at the bottom left in that black line, that solid black line, but all the different coloured zones are all the different scenarios depending on how all countries respond. And it's important to note that it's a global issue. No one country can solve this. It needs to be a global solution of all countries. So I note here an added complication that rich countries have emitted more and for longer than poorer, less industrialised countries. So we need to help them get more carbon efficient. And another bit of my reading is an Oxfam report found that between 1990 and 2015, the wealthiest 1% were responsible for more than twice the emissions of the bottom 50%. So we certainly have some work to do. So starting from that bottom scenario, which is 1.5 degree pathway, that's what we're trying for. That's what 198 countries signed up to in the 2015 Paris Agreement. But from my understanding, looking in the weekend, we're already at 1.4 degrees, unless this is an aberrant year, but they all seem to be aberrant. The 2 degree pathway above that's more impacts and more likely. Next pathway is current pledges and targets globally, so 2.1. Current policies, the actual policies that are there, 2.5 to 2.9 by 2100, that's an orange band. And then if we do nothing at all, obviously 4.1 to 4.8, which is pretty catastrophic. But it is just a graph. So what does that mean? So this slide is trying to explain what that means. So the top is temperature, the bottom is rainfall. The left, it's an intensity map, so the darker the colour, the more intense it's going to be. The left-hand column is 1 degree of climate change. We're already past that. The middle column's doubling that to 2 degrees. And you can see what doubling again to the right-hand column of 4 degrees looks like. So parts of the world may become uninhabitable, and it's going to affect everyone. And so I just added this slide in the weekend as another thing. Now, it's got lots and lots of data on it, so don't worry about that. But the one I wanted to point you to is this one, coral bleaching. So if we're at 1.5 degrees, that's 70% of the coral in the world is lost. But once we get to 2 degrees, we've lost everything, all coral. And again, from my reading, 450 million people worldwide in 100 countries live close to coral reefs and rely on them for their livelihoods. Coral covers only 0.5% of the ocean floor, yet supports 30% of marine fish species. So that's going to be a very large impact for a lot of people and a lot of fish. So that's the context we're living in. That's the risk to all our futures and the reason we need to work together. But as I said earlier, we've got to be positive, and I feel there's a lot of hope. But that's the hard part. So I'll go into some common terms now because there's a lot of jargon. I just want to make sure we're on the same page. So when we talk about carbon, these are all the different things we talk about. So carbon is shorthand, obviously, for carbon dioxide. So that's the CO2 in the air naturally or emitted during the burning of fossil fuels. It's a gas that absorbs heat and radiates some back towards the earth, preventing heat from radiating from the atmosphere. So it's like an insulation layer which is causing a build-up of temperature in our environment, obviously for global warming. So greenhouse gases, they're the various gases that can create global warming. So more on them a little bit later. And carbon dioxide equivalent, that's a key one, CO2e, the little e is important, equivalent. So that's putting all the different greenhouse gases into the same relative terms. And global warming potential, as it says there, is a measure of how much heat various gases absorb over time. Different gases have very different levels of absorption. And there's also embodied and operational, but I'll talk about that next. And there's another slide of jargon. So this is basically, there's upfront carbon, there's whole of life carbon, cradle to grave. So I'll go through these more shortly with some Green Building Council slides. LCAs, I mentioned those, they're life cycle assessments of a product or a building, carbon impact of it over its whole lifetime. And finally, EPDs, environmental product declarations. This is what I'm asking for, and actually Caitlin's asking every supplier for. So life cycle assessment of a product, which tells me the carbon information on that product. So enough of definitions. So what is carbon? So we have embodied carbon. Embodied carbon refers to the greenhouse gases emitted during the manufacture, transportation, construction, maintenance and disposal of materials at end of life, used throughout the life of the building. So what this highlights is that when we measure carbon in a building through its lifetime, not just when we buy a product or build the building, but it's through the whole lifetime. And as we've just noted, CO2 is not the only gas that contributes to global warming. So this slide shows that in more detail. Obviously on the left, the bottom, it's our common metric, carbon dioxide, because it's the most common greenhouse gas. But as you can see that, say, 1 kilogram of nitrous oxide is equivalent to 298 kilograms of CO2. And then it's a byproduct from the manufacture of nylon and fertilizers. But much worse, obviously, way over there, sulfur hexafluoride. Now that's in electrical transmission equipment, I believe. It's equivalent to 22,800 kilograms, so almost 23 tons of carbon per kilogram of that product. So kilograms of CO2e puts all these things in the same relative terms. There's a complication here as well. There's a lot of complications. These gases all happen to have different lifetimes in the atmosphere. CO2 is 300 to 1,000 years. Nitrous oxide is 150 years. And that sulfur hexafluoride is 3,200 years. So you're measuring these things in all different ways. But kilograms of CO2e is trying to use the common metric. So just a basic, wrong button. Just the basics of calculating carbon for a building. You have a quantity of a material, a volume, a weight area, or a weight, and you multiply it by an emission factor. So of the three examples, I just took to kilograms of steel. So you've got 100 kilograms of steel, 0.43 in this chart per kilograms of CO2e, and that gives you obviously 43 kilograms. Now, to do a LCA for a building, you do this for every single product in the building, and you do it through the whole life cycle of the building. So these stages, these are the carbon modules. This is the life cycle assessment in building. So there are 5 stages, A to D, from extraction of the raw materials way over here, and then transporting those raw materials. So that might be like iron ore coming out of the ground, transporting the iron ore to a factory, making steel out of that iron ore. So that's the production stage, where you're making a product. And then comes the construction stage, where most of us consultants get involved. So you transport that product from the factory to the site, of course. It's a transport, and then you put it on the site. So that's where we do the building. So myself as an architect, that's where we live a lot. So upfront carbon. Upfront carbon are these stages, A1 to A5. And we've gone through those sort of stages. They're also known as upfront carbon or cradle to practical completion. But they're obviously only part of the impacts. Whole of life is all of these stages excluding the operational. So this is embodied carbon across the whole life of the building. It excludes B6 and B7, which are the operational, which I'll talk about in a minute. So you've got the use stage here. So when you're using a building, you may have to repair the roof, you may have to repaint the building, repaint a house. So that's all the embodied carbon you use through the life cycle of that building. And then you've got end of life, when the building's deconstructed, transported away for disposal. Some of it may be buried, some of it may be burnt, some of it may be salvaged and recycled. And way at the end, D is what's called beyond the system boundary. So it's the potential to recycle and bring them back to raw material, which is using the term circular economy, and that's happening sort of more and more in the construction area, but there's a lot of distance to go there. So back onto operational is the remainder. So B6 and B7, energy and water. Basically the energy and water use of a building through its whole life cycle, through its 50 or 60 years of life. And then showing the intensity, this is showing the intensity of where carbon impacts. Obviously in extraction of raw material, manufacturing of products, and then refurbishment and replacement of things through the life of the building, because it's over such a long time. This is a construction, it's not quite as intense, and then you can see how it sits, but these are the main areas of concern. So this slide is showing how much operational and embodied carbon through the life of the building. Up front is obviously the most significant when you're building the building, and the light brown is the operational emissions, the water and the energy through the life of the building, and the green is when you periodically replace something, fix something or paint something, and then there's more at the end of the life. This shows a 60-year life because some of the tools have a 50. New Zealand's looking at using 50 to match the building code, as I understand it, and e-tools 60 years, and it looks like Letty in the UK uses 60 years. So looking at the same information in a different way, this is a cumulative graph. So the green again is embodied. It's a big hit up front. When you've just built the building, you've only got embodied. You haven't run the building at all. So the brown is the gradual increase over time of the use of water and energy. So you can see that after about 10 years, the ratio turns to roughly 3:1. But after by 2050, if you're saying 30 years, it changes at proportion to 50-50. So that gives us an indication of what we need to be looking at. We need to be thinking about embodied carbon in the short term because time is important. We haven't got much of it. So the next question is, how does that impact me or you? So I'm going to give you 6 reasons why you have to do something, why we in the building industry have work to do, and even small New Zealand at the bottom of the world must act now. And it needs significant changes to how we work. So reason 1 is we have a very high carbon footprint. And as Tina said, 39% of global greenhouse emissions come from operating the building and the materials within the building. And that breaks down like this: 28 operational, 11% embodied. It's lucky we matched up, Tina. And I read recently in a UNEP report that there are 3 materials that are responsible for 23% of global emissions: concrete, steel, and aluminium. are responsible for 23% of emissions, and cement production on its own is responsible for 8% of emissions. So the second reason is buildings have a long-term impact. So they go on for a long time. So the top graph shows that buildings of the past used to have a very high energy and water consumption. So operational carbon was very high. But buildings more and more nowadays are getting more and more efficient operationally. So embodied carbon is now a greater and greater proportion of what we look at. Reason 3, this one always surprises me. So we have a rising demand of buildings globally. As predicted by the UN, by 2060, globally the world needs 230 billion square metres of additional or constructed or renovated space. And that's equivalent to building New York City every 34 days for 40 years. Reason 4, the regulatory landscape. So New Zealand's committed to carbon neutrality by 2050, along with 70% of the world's economies. This is the MB framework on the left that they issued in August 2020. And on the right-hand side, that's the next 10 years of planning for reducing carbon in the construction sector in New Zealand. And this is a timeline from MB showing that in 2025, over there, we're looking at reporting carbon in our building consent process. So that's for all commercial and residential projects. Don't know what will happen with change of government, but we still have to do something by 2050. We still have to get to carbon neutrality. That's buildings of zero carbon impact. So even though we're a small country, quite green, far away from the rest of the world, we still have to do something. I looked it up, and we have 0.15% of global greenhouse gas emissions, which is very small. But our global per capita footprint is 3 times the average. And we're also the 4th highest per capita emitter in the OECD. So to remain competitive in international markets, we're going to have to get better. And last week, the European government passed a directive that all EU countries will carbon account for all buildings that are over 1,000 square metres by 2028 and all buildings by 2030. So that'll put a lot of pressure on us to be as green or greener. And reason 5, market demand and investor pressure. We'll find that investors and banks are driving this change. Commercial developers are reacting quickly. I already have large commercial clients like Precinct Properties. We have green finance that requires green ratings for all their buildings. And large corporate tenants now come with green requirements. And government organisations have a requirement to report on carbon annually by 2025 and show improvements. Our Māori clients have kaitiakitanga requirements. And actually, they've been the ones that have taken me on this journey. And reason 6 is simply, sorry, I didn't show that slide. Reason 6 is simply leadership and innovation. We can either get ahead and be a leader, make early changes, maybe not so early now, but or you run the risk of stranded assets, projects, products. So timing. Action is required soon. The next decade is critical. And this is showing, sorry for so many graphs, it is a bit hard. This is showing that if we make a 65% reduction, and that's on 2005 levels, by 2030 and net zero by 2040, we have a 67% chance of meeting the 1.5 degree target. But if we make 50% reduction by 2030 and net zero by 2050, we have a 50% chance. So that's what the Paris Agreement is, and that's what the Global and New Zealand Green Building Council's targets are. And if we have a linear reduction between now and 2050, the temperature rise will be greater than 2 degrees. So what we do in the next 10 years will make a very big difference. So there's limited time before a tipping point. So the steps that we're taking towards net zero, I'll just go through some quickly, are so passive design, site selection, thinking about sea level rise, flooding, building orientation, size of building, building reuse, insulation and double glazing. We reduce operational energy, reduce the energy and water use, make everything efficient. I'm relying on lots of services and engineers over there, Patrick. Eliminate fossil fuels, decarbonise, stop gas use, electrify everything, provide on-site renewables, things like photovoltaics, limit upfront carbon, as we've talked about, those stages A1 to A5, where everybody can help, and consider whole-of-life carbon. The other thing we're doing is benchmarking our projects against each other, competing with yourself. So this is what can occur when a project is measured for embodied carbon. The first column on the left is business as usual, a commercial building. The next column is reducing the cement carbon impacts with some cement replacements like slag, pozzolans and fly ash. Then more carbon efficient product selections, then maybe bio-based materials. And lastly, carbon capture, sequestering options and offsets. But you can see how the total carbon above the line has dropped significantly. That's the driver. We've got to drop that total amount. And this is just to be really clear, it's not normal emissions and then buy a whole lot of offsets. It's drive your emissions down to a level that we need to get to and then offset by getting to a level that achieves that 1.5 degree target. So it's a bit of a paradigm shift for us in the construction sector. So this is a slide of the tools we're using and where they come from globally. So as I noted earlier, we're using Brands' one-click LCA Quick, sorry. We're also using one-click LCA, and we've used eTool from Perth. We haven't used those other ones, but there's a number across the world. And at this point, to bring up the unspoken question that architects normally talk about, which is carbon impacts on business. So between 1990 and 2017, the UK economy grew by 60% in that period of time, about 27 years. But even though its carbon emissions declined in that period by 40%. So what we have to do is grow economies and drop carbon at the same time. So to sum things without graphs, so what we're doing in our practice. So this is a project called Pareo. It's in Otaki for Te Whangangarokawa. It's our fourth project. We started working here in 2009, I think it is. 4 buildings, 2,000 square metres, and a living building challenge project. So we did these 3 plus this one down here is the last project, and the central pedestrianised space, this car park. We've done this project before. We've done one over here, and I think that was on. Then we did this one as well. So this is just completed in May last year. So I'll get to the embodied carbon at the end actually. So this is the energy for the site. We've got 495 PV panels across those 4 roofs. You can see them in those various locations. They generate 105% of the energy needs of the complex. And we use the grid as a battery. So we generate, obviously in summer, the sun's higher, the days are longer, we'll generate more, and the reverse in winter. So in summer, we'll have excess generation, which will go into the grid, and winter will suck some out of the grid. But over the year, we have to prove, and we're in that certification period at the moment, where in May, we'll see how we're going. But I've got an app on my phone which can connect into it. It's well ahead of generation versus use. So that big PV array, we've got 4 EV chargers for cars. We've got resiliency with a battery bank in this location for the kaitiaki who work in here, and they operate 24 hours a day. So we've got resiliency. LBC requires resiliency for a week so that we can have parts of the project operate in a reduced fashion because batteries are expensive. And it's hard to get enough to run a whole project. So what else have we got? We've got a low light pollution campus, and so the next one's water. Water, we've got 2 areas of tanks. One area over here, there's one tank, one 10,000 litre tank here. There's 3 10,000 litre tanks here. So that's for potable water, so through UV and carbon filters. We've also got some of these tanks over here are not filtered, so they're for irrigation, flushing the toilets. We've got 32,000 litres of water underground here. It says 25, but it's actually 32,000 litres. And that's for irrigation through the year. So we store water in winter, use it in summer. And we've got a wastewater treatment plant. There's a septic tank system here and a 700 square metre dispersal field. So all wastewater is dealt with on site. And also these are rain gardens and wetlands designed by Rayton Associates, our great landscape architects, and they've used 32 native species of plants on the project. We've got some exotics for food production, which is an LBC requirement. Stu Farrant from Morpham, who many of you will know, was our ecologist on the site. We have to take the building back to pre-development hydrology. I think the hydrology was something like 14 megalitres of water a year off the site when we arrived. Pre-development hydrology was 3.64. We've got it back to about 4.6. And so the next slide's about waste. Oh no, next slide. So you can see our tanks. These tanks here, these tanks here, and you can see the PV panels across the site. Next one is waste. So waste is very difficult in New Zealand, and as Tina said, 50% of waste from construction fills up our landfills. Or should I say 50% of our landfills are filled with construction waste. So we had some great stories on this project. LBC requires 100% of soil and biomass to be reused, to diverted from landfill, 99% for metals, papers and cardboards, 95% for carpet and insulation, and 90% for everything else. So a minimum of 90%, which is extremely high for anywhere in New Zealand, let alone Ōtaki. So everybody lent a hand to it, and some of the stories on this page. So we found that the ceiling tiles could be composted, the offcuts could be composted, so they didn't have to go to the landfill. What else did we do? We had a Bodo cladding, so that was recycled. Lots of people took that away and made things out of it. Carpet and insulation have take-back schemes. So what happens is people like Teralana, they will collect stuff from site, they will take it back to the factory and put the waste offcuts into a new product. So it's a double win. You're recycling, you've got no waste going to the tip and not decomposing the tip. And you've got savings on the new product. It's not just all virgin product. And we have prefabrication of walls, roofs and floors that help reduce waste. And we also reused a lot of the soil on site and we did a lot of work to raise the level through this part of the site. Excess waste went down here over the fence into the neighbour's farm to fill a sort of depression in the ground, and this was our waste collecting area. So that was full. It actually it only got emptied just before Christmas, so like 6 months after site completion. But the stats are, 3,060 tonnes of waste for the project, 2,200 for soil, but altogether we had 99.9% waste diversion. 3.815 tonnes went to the landfill. And that's a lot of carbon saving there, and that's what we would need to be working towards. Yes, and materials. Caitlin, again. So Caitlin's our materials researcher. We have to, Caitlin checks everything to 100 parts per million, and there's a thing called the red list. So there's about 1,000 CAS number chemicals. There's an example of a CAS number chemical. 9002-88-4 is HDPE, which is an alternative to PVC, which is, we're not allowed to use PVC on any LBC project because of its how it's produced and how it's disposed of. And HDPE is a good sustainable alternative. So we use that. Lots of CAS numbers to get rid of. And so every product is investigated for those 1,000 CAS numbers. So we have no PVC, no CCA treatment, which is very hard. It's all MCA treated. We designed raised timber floors instead of concrete slabs. We minimised steel. So here's a section of the project. So PV panels, of course, 495 panels. This is our red list. We have to get 90% compliance with the red list. Very hard to do. It's taken us, Caitlin's been with us for 7 years and we've done 5 5 projects. So it's a lot of research. Ventilation, lots of natural ventilation, 24 skylights in the main Te Moana or Rakawa building. And then there's cedar louvers for natural ventilation through all the buildings. The waste diversion, we just talked about, landscape, food production, and Rate and Associates right through the buildings. Rainwater collection, here's a section through the wetland where that 32,000 litres is stored. It's underneath a rain garden. And then our wastewater, blackwater treatment, and we manage all stormwater on site. So, quite extreme, but actually all operating quite well at the moment. In terms of carbon here, so our full, we did an e-tool, full life cycle on this. So embodied carbon is 810 tonnes of carbon dioxide through all stages, A to D. So that equals, if you divide it by the 1,784 square metres of the buildings, it's 438 kilograms of carbon dioxide E per square metre. Just as a point of reference, that's my most recent looking at the RIBA, the Royal Institute of British Architects, data is they're aiming for 750 kilograms per square metre by 2030. So we're already well under their target for 2030. And that's a 48% reduction on business as usual. The other project, which you may have seen, as Tina mentioned, this is the Living Pa at Victoria University. So it's a 3-storey, 3,000 square metre building that's you can't quite see it. Wharenui, it's just in there somewhere. And it's for Te Ao Māori, Māori Studies at Victoria University, and it's connected and supports the Wharenui. Also, there'll be the sustainability office and PVC Māori in there as well. You can see the PV array. So there's on this project, there's, how many is it? I've just forgotten. There's 551, that's right, 551 PV panels, a 220 kilowatt peak array. So that will generate all the power for the building. A third of the power of the building is used by the kahini, the kitchen. It's predominantly naturally ventilated. We've got the same levels of recycling that's happening currently on site. We're struggling in one area, but we're working hard. Well, LT McGuinness are working hard. Cladding is timber, the framing is timber. And you can see the PV arrays. There's some steel supporting these. We've had to hang the PVs off the side of the building because we need more area of PVs than the building footprint of 1,000 square metres. And you can see we've got elevated planters, which I'll talk about on one of the next slides. And they support plants which grow up the building and evapotranspirate some of the wastewater. So this is from the Wharenui side, the Aotea. We will relocate the Waharoa, and then there's another 60-metre long planter along here in a walkway. The idea is that the building will be more transparent, the ground floor, so you'll be able to see the Wharenui, which has been concealed behind the 5 colonial houses that have been there. And largely CLT, cross-laminated timber, and LVL, laminated veneer lumber, mass timber building. It's got 900 cubic metres of CLT in it and significant amount of carbon sequestration. This is the hydraulic cycle of the building. Essentially, capture all the roof water and use it, put through carbon filters and UV filters to make it potable. There's other water that's kept for irrigation. We collect grey water, so that's water off wash-hand basins and showers. That's in a couple of 10,000 litre tanks, I think. And that splits 2 ways. One goes to the planters on the side of the building. One half of it goes that way to those things. And then the excess from those goes to a land-based stepping planter system on the street. And then the excess from that goes into the blackwater treatment plant, the wastewater treatment plant. The other half goes to flush the toilets. We have vacuum toilets like in a jet aircraft. They only use 0.7 litres per flush. And then they end up there. Now, the next thing that happens is out of the blackwater treatment plant, we take 352,000 litres of water a year and flush the toilets in the Murphy building. So essentially no water goes off site until it's gone through, some of it's gone through another building. And what else is happening there? We've got evapotranspiration, you can see from the plants. And so it's quite a feat to make the water work. It's a very difficult site. This is a photo of it about 6 months ago. You can see the big long, these are the LVL columns, 12 metres high. Biggest pieces of LVL in the country. They're shaped like a T. That's 1,200 wide by 300 thick by 12 metres high. 27 hours of CNC time to join them together. And there's 1,088 screws connecting each one of those columns. That's the vertical structure, it's the LVL. The horizontal structure is all this stuff called CLT. These are some photos from Andy Spain. Got a raised floor system. You can see the little blocks. It's 150 mils high, and that's where a lot of our services run, and then punch through the floor to the waffles below. This is sort of quite a good shot. It shows a section of the building. This was just before Christmas, and you can see the CLT floor slab on the ground floor, and then a little bit closer up you can see what CLT looks like. It's laminated and crossing directions, and it's a bit like a licorice all sort, but quite thick. And then one of our last bays where they're dropping in the panels, moving some of the columns around. And then again for this project, carbon, 1,294 tonnes for the A to D, which is 421 kilograms per square metre. So a very good result, and a lot of sequestration, 43% down on business as usual. And when I say business as usual, when you do an LCA through eTool, they do a whole model of a normal, so you can see how much you're saving. And then to finish, just some of those thoughts of what we can all do if we go away, and if we're working in construction, what you can do, and if you're not working in construction, if you employ someone, you can ask for. So act now, like I said at the beginning, collaborate with people, because it's not just about one person doing the work, it's about a whole lot. Build less. So probably one of the best things you can do is to take 10 square metres off a building, 5 square metres off a house alteration, take out another ensuite, get rid of those ensuites. You can build less, build with less. So simplicity of detailing, to all the architects out there, keep it simple, because if you have less stuff in the building, you've got less carbon. Fix what we have, a bit like just through that wall, the library is being rebuilt. There was an option to knock the whole thing down and build a new one, but by keeping the concrete frame, there's significant carbon savings. So we're going to have to reuse buildings, reuse parts of them, reuse all of them. Carbon literacy, upskill the team. I made a wee mistake in that, took out an S. And upskill the team and make sure everybody gets carbon literacy. Understand rough carbon, like we'd understand rough cost, and that's still something I'm still learning about. So go out and do an LCA if you're a consultant. Try one. If you're a client, ask for one. Learn what's carbon intensive, steel, concrete, aluminium. Learn what sucks up carbon, something that's biogenic. Decarbonise everything. So we've got to move away from gas, we've got to electrify. Ask for those EPDs, get that carbon data, give it to brands, because they're building a database. They've got a database, and there's a whole discussion about who will own the New Zealand database. So give it to brands. Focus where your materials come from. That's about the embodied carbon, the transport, A2 and A4 of how the material gets to you. And ask about product recycling, because that'll save carbon. Raise awareness, and then again, act now. So thank you very much.
Well, thank you very much, Ewan. That was fantastic, and the graphs were very helpful.
Good.
So I think we've got 10 minutes now. If anyone's got any questions, there's a roving mic, and just raise your hand. Oh, there's one at the back, there.
If I can answer them.
Kia ora koutou, my name is Felicity Wong from Historic Places Wellington, and in the recent district plan hearings we were the only submitter to turn up and talk about the kinds of things that you're talking about. And last week it was incredibly distressing that the councillors voted to delist the Gordon Wilson flats in the lead up to the Victoria University Te Herenga Waka sending it to the dump.
Yeah.
Do you have a comment on that enormous social housing building, which I might add is not earthquake prone? It's 88% NBS, but it's got panels that fall off the front and it
Yeah.
clearly needs work, like a new facade and the covers
Well,
and balustrades.
Yeah, with my argument about the library, there's a lot of concrete in that building. But I know we've met the Gordon Wilson's family, and they've been over and we've showed them through the fence that building. But I'm unsure. I haven't got much comment in terms of carbon because there's so much other political discussion on those buildings. But there is a lot of carbon in that concrete.
They hid it from me. I'm going to go for a little bit of a less spicy meatball, if possible, or maybe not. Have you done any work to validate a lot of the work that you're doing here? I see is the LCA stuff, which is really super valuable. Have you done any work to validate that the numbers that are going into the LCA tool are representative of what actually happens on site, or do you have plans to sort of collect that data and actually confirm that what we're seeing is?
So that's about. Are you saying about updating your LCA at the end of the project? Or are you talking about the data that goes into your LCA?
Yeah, it's kind of more like any model, right? All models are wrong, some are useful. Have you done anything to confirm that the amount of the amount of carbon that the LCA says that you're producing is going to be as close as you can sort of possibly get it to be to the... Because I work in the construction industry as well, and you know that as you get closer to final completion, you have all these design changes come through at the last moment, and that's sort of going to knock your numbers around a little bit.
Oh, so there's a few comments there. One good living building challenge is incredibly difficult, incredibly challenging. But one of the good things about it is you can't change anything. So I go onto the site and tell the contractor nothing's allowed to change because we've done all this work. Caitlin and I have done this work, which means Caitlin's done the work. We've done all this research on those materials. And there's quite a lot of work, and it takes a long time to get compliance of an LBC, something that get red list compliance. So our spec is we say you must use all these products. There's no option. So in that sense, the LCA is not going to go very far away architecturally. I should context that with architectural. It doesn't go very far away from where we started. On both those projects, there's a little bit of a tail end process of redoing the LCA, amending the LCA for any significant changes. But Pareo, the one in Otaki, didn't have very many changes that I can think of right now. And the Living Pa, some, but still very minor. Probably the area of the biggest change is probably building services, because that can be quite difficult, but it's some challenging stuff. But the other thing I'd say also about data is I'm on a brands panel and trying to talk. They've got quite a lot of data, but carbon data is all about a hierarchy of information. So you'll either have an EPD with exactly the information on that product that's available here, which will tell you all those, the full modules, everything for that product. So that's your gold standard information. But you might not have an EPD, you might have an MSDS sheet, materials safety data sheet. So you might have some information from that. You might not have everything. Or you might go to a national average for a product, or you might go to a global average for a product. So there's a whole hierarchy, and people, product suppliers can move their products up that list by spending some money, getting an EPD, which can be expensive, but they last for about 5 years. So there's going to be a whole process of managing the data. At the moment, each of the tools has different databases. So we're trying to advocate for a single New Zealand database. It will come, hasn't happened yet, and there's still a couple of potential sources for that database.
Kia ora, Ewan. Thank you very much for that presentation. It was so graphic. It's fantastic.
Thank you, Nick.
My question is, you might be aware that in places like UK and maybe Europe, architects are getting briefs for buildings to last 300 years. Now, no, that's not going to meet the 2050 target, but do you think that the lifetime of a building, if it was to be extended, would that impact on the data if the building's there for longer,
Yeah.
it's obviously better. Have you got a graph for that?
I'll get you one tomorrow. A couple of things. One is I was on a awards jury last year and we went and saw a house and the architect said this was quite a big house, a very big house, like a very, very big house. I can neither confirm nor deny. I don't want to get into trouble. But it had a lot of concrete in it. It was a very big house. And the argument from the architect was the brief for this house was for it to last 200 years. And therefore they were doing really well carbon-wise. So I didn't know what to say at the time, but I rang a friend, Katie Simons, who's responsible for embodied carbon with the Building for Climate Change program. And I said, well, we're using 50 or 60 years, depending on where you look. But she said, that's only a reference. You've got to use a number somewhere. It's only a reference. But we don't expect the living part to only last 50 years. We expect it to last 100 years or 150 years. But it's very hard to tell. So yes, you do want buildings to last a long time and you do expect them to last a long time, but those numbers of 50 or 60 years is a little bit of a misnomer, I think. But it's a point of reference data. Thank you, Nick.
Kia ora tātou, ko Ash toko ingoa. Thanks for tonight. I think one of the things that dropped really intensely was the New York every 34 days.
That one's still shocked.
And I was just wondering if anyone, or you know of anyone that's doing any work in terms of like the carbon intensity. So obviously if we build a really efficient, low carbon building, but one person uses it once, it returns to being a very carbon expensive building. And I was wondering if you guys know of anyone who's matching it to like usage hours or human hours in the space or any of that kind of work.
Yes. So when I started putting stats on our website, you start trying to think of what is a common metric. So the square meters of kilograms of carbon per square meter is quite a good one, but it's not very good if you've got a 1,000 square meter house and there's 2 people in it. So you might have a low density of carbon, but you might have a hell of a lot of people, only 2 people in a really big space. So I have heard it, I haven't done it myself, but I heard about people saying per person sometimes. So and I think it's just one of these things, there'll be growing metrics. I haven't seen anybody use it, but it's one of the things that's quite tricky when you go on the awards programs, there's now carbon data that people are putting in, but there's all sorts of things like some people do upfront only, some people do A to C, some people do A to D. And then the granularity, how much you measure, how much of the building. Some people only measure the concrete frame or the structural frame. Some people measure the whole skin of the building. Some people measure internal walls, bathrooms. Some people put services in, not operational in. So we haven't got to a point of agreeing what our common metrics. It's like your stars on your washing machine. How many stars? We need to start agreeing what that's measuring. Not everybody having their own star system. But I think that's the one that will come out, which is carbon per person in a house, maybe, if you do a big house. But generally, I'm focusing on the square meters.
Thanks, Ed.
But I'm happy to hear anybody else's ideas. And I think it'll just evolve.
We've got 3 years of really good data from 257 across the road, like burnout and carbon.
Oh, I see. Yeah.
That should be something.
Yeah, that'd be good. Be good. Was there a...
I don't know much about 3D printed architecture, but is that done with concrete?
I have seen a video of somebody printing a house in concrete. I don't know where it was, but
So how does that, are they developing a low carbon concrete for that, or how does that sort of work in the future?
I don't know anything about what that concrete is, because it'll probably have a whole lot of drivers that are more about it making flow out of these nozzles. Because when I've seen it, it's like toothpaste, and they're running around and just building up layers of toothpaste.
Ideally they're trying to look at an efficient use of concrete to make most of the structure in terms of carbon.
I would tend to build a house out of timber, because then it'll sequester rather than, because concrete's always going to suck up carbon. About concrete, so I think you can get, I saw somebody talking recently about 40% cement replacement, because cement's where all the carbon is. Mm-hmm. And so you can use this stuff called fly ash, I forget what it is, fly ash and slag from steel manufacture. Some of it they scrape off chimneys, and the other stuff's a byproduct. Pozzolans are natural clays, out of the ground, and there's some in the Bay of Plenty area. I don't know if they're being used yet, but there are people that are getting to 40% cement reduction, and that's the best thing you can do with concrete. Look at those alternatives.
So would 3D printed architecture sort of clash with...
Well, yeah, 3D printed concrete house is going to be naturally just...
So there's, the future of that is...
well, hard to tell. Hard to tell. They look like very big printing. I saw this video of them printing one. It looked very strange, but fast once you've got it all set up. But I don't know how you change it. You get the same.
I'm asking because a local guy has just won. He's just won he's just won first in the world for 3D printed architecture for low cost housing and all.
Oh, right.
And and he's coming back to Wellington
happy to see it.
now. And I'm wondering if it's just an idea or a concept, if there's any way that it can even match what you're talking about in terms of...
Yeah, I mean, there's going to be advantages of speed there. If it's a mechanised process about building a whole lot of houses for people quickly, so there's going to be an advantage of time. I'd be really interested to see what the carbon side of it was, because the way it was built out of these layers of sort of tubes of concrete, you're still going to have to put something on the inside and the outside to flatten it and weatherproof it a little bit more than just rough concrete. So it'd be really interesting to see.
Wow. I think that's a good point to wrap up for the night. And please continue these discussions in the foyer over some tie and some drinks. And thank you very much for your time and all your energy into putting together this presentation. So everyone, please join me once again in thanking Ewan.